Good day everyone. I'm Niranjana Arulnambi, currently in my final year of biomedical engineering at Rajlakshmi Engineering College, located in Chennai, India. And today I'll be presenting our systematic review titled Grasp Strategies of 3D Printed Soft Robotic Actuators, a systematic review of materials, mechanics, and mechanisms. So, here's the flow of today's section, and I'll be walking you through each section and highlight the key insights from the 46 papers that we have actually reviewed. So, what is a soft actuator? A soft actuator is a flexible device which is made from material like silicone, hydrogel, or an elastomer. They deform when exposed to stimuli. This stimuli can be either a pneumatic pressure or an electric field, or even magnetic fields, or even heat. Their biggest strength is that they can mimic biological motion, especially the natural grasping behavior of the human hand. They conform to irregular shapes, distribute forces safely, and avoid the damage that rigid grippers tend to cause. This makes them ideal for tasks that require delicate interaction, such as medical manipulation, fragile industrial assembly, and bio-inspired robotic systems. So, traditional rigid grippers generally struggle with irregular shapes and delicate materials. Soft actuators solve this problem by being compliant. They wrap around objects instead of forcing objects to adapt to them. A notable study by Wang et al. Demonstrated a bio-inspired pneumatic finger made from SMP PLA achieving a 24.9 times stiffness change from 20 degrees Celsius to 60 degrees Celsius. This kind of tunable stiffness is exactly what is needed for controlled human-like grasping. Applications include robotic surgical tools, industrial pick-and-place systems, and adaptive grippers for complex environments. The goal of this review is to systematically examine recent advancements in 3D printed soft actuators, focusing specifically on grasping strategies. We aim to first identify the key material systems that support conformal grasping, second, examine the actuation mechanisms that enable the natural motion, and third, evaluate the various sensing capabilities that are integrated into soft actuators. We also like to highlight how new materials and printing technologies are addressing common challenges such as poor load capacity, low precision, and limited durability. The methodology of our survey was based on the PRISMA guidelines, and we reviewed 46 publications published between 2015 and 2025 based on the following criteria. First, it must involve either 3D or 4D printing of soft actuators. It must focus on the grasping, manipulation, or conformal contact, and any actuation type that was implemented was included. To name a few of them were pneumatic, hydraulic, electrical, magnetic, chemical, or even hybrid type of actuation. Each paper was analyzed across materials, actuation strategies, fabrication techniques, mechanical behavior, performance features, and application use cases. Moving on to the results that we obtained, a simple overview is that we made a classification framework where we structured the literature into four categories: actuation principles, fabrication strategies, performance features, and applications. So the various actuation principles, as I said before, were included. Fabrication techniques spanned from the use of DM, DIW, SLA, and polyjet strategies, and key performance and design features included the use of integrated sensing or variable stiffness and even programmable motion. Various applications were arrived at. Some of these included soft grippers and some were involved in medical rehabilitation. There were also a few papers that focused on the safe interaction between humans and robots. The flowchart pictured here is an expanded classification of the literature reviewed. The four pillars that we had identified were actuation principles and materials, fabrication techniques, key performance and design features, and applications. Under various actuation principles, we further categorized them into pneumatic and hydraulic actuation, electrically driven actuation, stimuli responsive actuation, and then the use of hybrid smart materials for actuation. Under fabrication techniques, we explored the use of additive manufacturing and design for additive manufacturing with an exploration of the key fabrication challenges faced for soft robotic actuators. And then, looking at the key performance and design features, we found that programmable motion, sensing integration, and variable stiffness control and biomimetics were the major trends that came up. In applications, we found that grasping and manipulation, medical rehabilitation, locomotion, and use in haptic devices and use in micro robots were the trends that we were able to observe. Let's examine the key material innovations from 2023 to 2025. First, Fang et al. Developed a foldable TPU actuator using BIFE structure, that is bio-inspired interweaving foldable endomysium structure. This demonstrated excellent repeatability over 5,000 cycles with stable pressure feedback for integrated sensing. Song et al. Created a hybrid multi-material DEA combining soft and stiff resins. The soft dielectric resin achieved an impressive 145.3% strain. This enables navigation across diverse multi-environment situations. Kim et al. Used TPU along with PLA reinforcement to create artificial muscles with complex origami bellows. The key achievement here was stable performance even over 10,000 cycles while pulling significant loads. Chen et al. Pioneered biodegradable actuators using cuttlefish ink nanoparticles, enabling humidity and light-driven deformations in an environmentally sustainable way. Finally, Antonelli et al. Developed a silicon TPU hybrid structure for a bio-inspired tail actuator, achieving 11.9 Newton force output, showing how reinforcement can enhance performance. Continuing with materials innovation, Yang et al. Fabricated origami actuators using TPE, enabling both fast swimming at 0.6 body length per second and terrestrial crawling at 20.66 millimeters per second, demonstrating amphibious capability. Stano et al. Tackled a critical challenge of stiff-soft interface addition. Using optimized geometry and annealing, they achieved 3.8 megapascals tensile strength, enabling 120-degree bending robotic fingers. Zhou et al. Developed stretchable foam using DLP printing, creating structures that withstand 40% compressive strain and 1.57 megapascal tensile strength. The porosity control enabled customized stiffness gradient. Huang et al. Created thermoresponsive hydrogels using GEIMA, that is gelatin methacryloil, and PNI-PAM, that is poly-N-isopropyl acrylamide gels. So these were commonly used biopolymers which were made use here. These are also biodegradable with a repeatable 5.5 centimeter inverse curvature bending. Finally, Gunawardene et al. Achieved multidirectional actuation with TPU, achieving both 30% extension and 100-degree bending from a single design at 350 kilopascal pressure. Moving to the mechanics and actuation mechanisms, the previously seen publication Fang et al.'s Buffet structure enabled multidimensional motion with integrated sensing. It was able to achieve 1 mm displacement sensing accuracy with excellent cyclic reliability. Song et al.'s modular robots were able to achieve 145.3% linear strain and demonstrated collaborative capability where multiple units were able to drag 100 times their body weight. Kim et al. Used a sophisticated motorized actuator with HSA shafts and origami bellows, which was able to achieve 29.5% maximum stroke and 75.2 newtons of pulling force with 10,000 cycle durability as seen before. Chen et al.'s biodegradable design used humidity and light stimuli for programming deformations with 5.31 centimeter inverse bending curvature. Antonelli et al. Seahorse-inspired tail actuator follows a logarithmic spiral structure with pneumatic actuation. It was able to achieve 154.5 mm full distension at 1.8 bar with 11.9 Newton force and 74.9 millisecond activation time, which is an impressive speed for pneumatic systems. Young et al. Created an amphibious robot using multiple origami types such as Z-shaped, twisted tower, pelvic fin, and coiling actuators. The performance metrics include 0.6 body lengths per second for swimming and 20.66 mm per second for terrestrial crawling, plus successful insect hunting with 0.25 second trunk projection. Stano et al.'s stiff soft interface optimization using T-shaped geometry and thermal post-treatment enabled 120-degree bending angles in robotic fingers with a 48% adhesion improvement. Zhou et al.'s porosity-controlled monolithic actuators were able to achieve 77% linear actuation strain with a 14.3 degrees bidirectional bending, and impressively, all this were achieved only using 25 kilopascals of pressure. In summary, 3D printed soft actuators have evolved from being just passive, compliant structures to actively adaptable systems that are capable of true conformal grasping. The current state of the art combines fast pneumatic or hydraulic actuation along with magnetic or thermal shape locking and stiffness tuning, which enable robust handling of fragile and irregularly shaped objects. However, certain challenges do remain. Cyclic durability at printed interfaces, slow actuation speeds for non-pneumatic stimuli, and the need for fully embedded closed-loop control systems still do remain. Future breakthroughs will depend on three key developments. The first one is durable, self-healing sensing skins. The second one is fast-switching hybrid actuators under 500 milliseconds. And the last but not the least one is scalable multi-material 4D printing platforms. This positions soft robotics at a critical inflection point, where laboratory successes can finally translate to a real-world adoption in medical, industrial, and bio-inspired applications. And thank you for listening.